Alright, gang, here we go. So this is Physics, Unit 2, Part 2, Projectile Motion. So in Part 1 we talked about vectors, we talked about vector math, we did some complex and simple vector problems. We took vectors and we resolved them down into their individual components, both x and y. Alright, and so now we're going to take all of those ideas and apply to them to the specific case of the motion of a projectile. Hence projectile motion. Alright, so let's think about this for a second. Suppose we have two coins and they fall off a table simultaneously. Alright, well that's easy. So two coins, we push them off a table. Okay, one coin falls straight downward and the other coin was slid off the table horizontally and landed several meters away from the base. Alright, so it looks like so we've got like a table here, and in physics it's almost always easier to draw us a little thing. So we've got, so there's one coin, right? And then the other coin, so one coin just kind of went do and fell straight down, right? And I'll bet it made that noise, do. And then the other coin was slid off the table, so that means it came out with some horizontal velocity, right? Straight out. So that means it came out here, so its path would have done something like this, right? That makes sense. So its path would have done something like this because gravity is pulling it down, but it's also moving to the right. All right. So which coin would strike the table first? Or which coin would strike the floor first? Well, we know that two objects that are dropped from the same height fall with the same acceleration. So therefore, they'd have to hit the ground at the same time, right? Because they're both the same object. They're dropped from the same height, and both of their vertical velocities are the same. They're both 0, right? They're both in free fall. The one difference is the one that was slid off the table has a horizontal velocity. Now that horizontal velocity is going to change things for us, but for now we can just kind of move on with our lives. Okay. So anyway, so one's going to the right, one's falling straight down. Okay, so the one that goes and falls to the right is going to land at the same time as the one that fell straight down. Okay, would you change your answer if the second coin was moving so fast that it landed 50 meters from the base of the table? Why or why not? So what if we how about this? Instead of we think about coins, think about this. What if we had a gun and we put a bullet in the gun, right? And then we had a bullet at the same height, right? So we got a gun, we got a bullet, and they're at the same height. And we set up a mechanism, and when I'm there in class, I'll show you this, okay? We've got, not with a gun, but with a contraption using ball bearings. It's pretty slick. But anyway, so we had set up a contraption that the gun fires the bullet at the same time it drops the bullet. Okay, so it fires and drops at the exact same time. And let's say that we've got a long enough gun range so far that the bullet can travel around the curvature of the earth, however far it needs to go before it just falls and hits the ground. Because as soon as we fire that bullet, gravity is going to start pulling it down, and there's nothing holding it up, right? So gravity is going to be pulling it down. So the path of that bullet is still going to be dropping as it goes. Okay, it's going to be forward really fast. It's going to have a really high horizontal velocity, but as it goes, it's going to be dropping. Okay, now if you think about it, what we've learned so far in physics is that when two objects are in free fall, meaning they're falling with an initial velocity of 0, okay, and we can neglect air resistance, is that they're going to fall at the same rate. They have the same acceleration downwards. Okay, so both these bullets are going to be going, and they're going to be falling and hit the ground at the same time. It's kind of bizarre, okay? So these things, when we launch something into the air, it doesn't matter what angle we launch it from, we call it projectile motion. Okay, so there are objects that are launched in the air. Tennis balls, arrows, baseballs, wrestlers, my kids when I launch them off the couch, etc. Stuff like that. Okay, and the problem is here is gravity is constantly pulling down, because we know that gravity is 9.8 meters per second square all around the earth, and pretty much we assume that anywhere humans live, okay, within Earth, it's 9.8 meters per second squared. It's pretty much stable at that value, which is pretty handy for math stuff. Okay, so for our class, we're going to assume that air resistance can be ignored. Okay, we're just not going to worry about air resistance. If you do have air resistance, it's simply going to make your path shorter. Okay, so here's a ball. Here's a girl hitting a soccer ball. Okay, and so this is a projectile motion. She hit it, and so when she hit it with both a vertical force, right? A vertical force to hit it straight up, and then she also hit it with a horizontal force to hit it to the side. If she only hit it with a horizontal force, then the path would have gone something like this and then dropped, kind of like that penny, right? If she hit it with the vertical force only and not the horizontal force, it would have gone straight up and then straight back down. That's no good. All right, so because we know that this is the path it took, it had to have some amount of vertical and some amount of horizontal, and so therefore we got this guy when we combine those. And for those of you, those keen physicists in this would recognize this vector here as the resultant, right? It's the combination of the two. All right, so here's our resultant vector. So anyway, so this guy goes up, and the resultant, so as it's going, okay, gravity is going to start going. Remember, part of it is a velocity, you know, v in the y direction, and this would be our v in the x direction. Now, the gravity only acts in the downward direction, right? Okay, this would be gravity. We'll call that g. So gravity only acts in the downward direction. This is not going to affect f delta, or this f vx. So when we get out here at the peak, how much vertical velocity do we have? Well, maybe we'll start right here. So let's think right here. All right, so we're halfway up or so, okay? And we've got our, I made my resultant kind of long here, but that's okay. So so let's graph our y and our x. Well, we're only halfway up, so that means our y velocity has to be half as big, right? Because when we get up here, we know the vertical velocity has to be 0, okay? So that means that our y velocity has to be about half as big. This is really obnoxious, okay? So that's our new y velocity. Well, how was our x velocity affected? Well, our x velocity is not affected by g because they don't share any common component, right? G is only in the y and x is only in the x. Okay, so our v sub x going this way should be exactly the same size as it was before. All right, and then when we get to the top, there's absolutely nothing pulling us up, okay? But this guy is going to be the same size going that way. Halfway down, okay, now our vertical component is going to be pointing down, but it should be exactly, oh my gosh, it should be exactly opposite of this guy here. And our v sub x, again, is unchanged, okay? So anyway, so that's, if you can imagine kind of what's happening to our vectors, that'll get you a long ways towards understanding what this lesson is about. We'll talk about this a little bit more here in a second. All right, and then with air resistance, notice that if we have air resistance is going, if we imagine our soccer ball, air resistance is going to push against it in whatever directions we're headed. So if we're headed generally this way, right? So we're headed generally this way, air resistance is going to affect it more here and here, right? So that means our v velocity, whatever force we use to hit our ball in the y direction, is not going to be as effective. So it's not going to get as high. See how much lower our air resistance path is? And then as we are moving to the right, we're stopping our ball this way, so our ball cannot move as far horizontally either. Okay. So that's the effect of air resistance. Now, mathematically, it gets a lot more complicated than that, and so we're just going to ignore it mathematically. We're just going to say air resistance isn't really a thing. All right. So here's a long jumper. Okay, it's a runner. She's a long jumper, and she runs, and then she launches herself. Okay, so it's the same thing as the ball there. Okay, so she launches herself, and so you know that in order for her to successfully launch herself, she had to have had two vectors, right? She should have had, if this was her velocity right here, this was her original velocity, you know that there had to have been two components to it. There had to have been some part of her that launches her to the right, that's that v sub x right here, and there should have been some part of her that launched her straight up, that's that v sub y. All right. So overall, when we combine these things, remember to add vectors, we go tip to tail. So here's our tail tip, and we can move our v sub y out here. All right. And so then our resultant vector goes from there to there. Okay. So this would be our v initial, all right, or our overall vector, our resultant. All right, so in this figure, it's kind of the same idea, it's just kind of graphing it all out. So when the i's, remember, start for initial, right? We use i's for initial and f's for final, so these are all initial vectors. All right, v sub y I is how you would say that. So that's the vector for velocity in the direction of y. Okay, so that means it's going up and down, and it's the initial vector. And then this is v sub xi. Okay, and so that's the vector velocity in the x direction times I. All right, and then here's your resultant, and then between the two, this is our theta. We almost always measure theta against the x-axis. It's just kind of the common thing. So, and then remember, we talked about this in part 1 video here, and when we talked about vectors, these two mathematical relationships that we can calculate v sub xi and v sub yi, or just generally, we don't even need the i's, okay? It could be f's, it could be just nothing, is equal to the resultant vector times cosine theta. It gives you v sub x, and v sub y is the resultant vector times the sine theta. All right, so make sure you make note of these in your notes. Those are an important relationship that we're going to apply quite a bit here. All right. So let's talk a little bit more about projectile motion. So it's going to be broken up. We're going to break it up into two parts, the horizontal motion and the vertical motion. This slide focuses on the horizontal, so we're going to talk about that, and then we'll jump to the vertical motion. All right. Now, horizontally, we already established our ball, you know, and that girl, she hits the soccer ball, it goes up and it goes down. Her vertical velocity does not get affected by gravity, and we're going to assume air resistance negligible, so therefore there's nothing affecting or slowing down the horizontal movement of our ball. Okay, that's what we're assuming. Okay, it's not necessarily true, but it's true enough. Okay, so anyway, so there's nothing slowing down our horizontal velocity. So in these problems, because there's no acceleration to our horizontal velocity, remember acceleration is defined as the change in velocity. Okay, because there's no change in that velocity, the horizontal velocity has to be constant. That makes the math super easy. Okay, so that means our v sub x I is always going to be equal to our v sub x f, always. Okay, because it's constant. Okay, so how would the horizontal distance traveled change during successive time intervals of 1.1 seconds each? Well, the distance traveled for each time interval should be exactly the same, because the velocity is always the same. So if we say that we move 1 meter in 0.1 seconds, that velocity is not going to slow down or speed up because there's no acceleration on it. So it's always going to remain the same. So every 0.1 seconds we've traveled 1 meter. All right. So here's your math here, and most of this stuff is just kind of more confusing. All right, so really all you need to know is like this guy right here, okay, is what we had on the last page, right? V sub x is equal to v sub xi, right? That's kind of what we established up there, and that's equal to v sub I cosine theta, right? That's the exact same guy as right here. All right, so those are the exact same things. All right, and so because this value here is constant, okay, and we're always staying with the same angle, that means this whole thing is going to be constant. All right, so that's an important fact. All right, so we can take all this and we get this formula here. We don't have to worry about deriving it, but we're just going to run with it. All right, so delta x, or the change in your x displacement, is always equal to your velocity, whatever your initial launch velocity was, because that's usually what we're going to measure. We're going to be like, how hard did you launch your object or jump your object or whatever it is, v sub I, times cosine of whatever angle off the ground it was, times delta t. All right, so this is your big important delta x formula. All right, so make sure you make note of this guy here. Off the top of my head, I'm sorry, I don't remember if it's on the note sheet or not. So you might want to check the note sheet and see if you have to memorize it. All right. Vertical projectile motion, life gets much more complicated, and that's because acceleration is a thing. Okay, because acceleration is falling, we get negative 9.81 meters per second squared. So our vertical velocity is going to be increasing as we go down, okay, or decreasing as we go up. Okay, so essentially, you can remember we spent like a good chunk of last unit talking about free fall. That's essentially what this is. It's an object in free fall that is moving horizontally. That's all it is, really. Now, it gets a little bit more complicated than that, but like essentially that's the crux of the matter. So you don't have to think about it too much more. It's just one additional step. Okay, so, but that also means that a lot of our kinematic equations you're also already used to using apply perfectly well here. The only thing that might be a little confusing based on these guys here, so these are these are essentially the kinematic equations. You might notice these sine thetas thrown in. Now remember, these sine thetas came from this guy right here to convert our resultant into the component in the y direction. Okay, so remember how on your equation sheet how it says like v sub x and d sub x and stuff like that, and it was always referring to the x direction. It's trying to get you to realize that all of those things are moving in the same direction. That's why those equations are written the way they are from the last unit. All right, that's why I told you need to get used to reading them the way they are. All right, on that note packet. So let's analyze these real quick so you can kind of get an idea. So this is v sub yf. So that's the final velocity in the y direction. So that's the final velocity in the up and down direction. All right, that's v sub yf is equal to v sub I. So that's the initial, that's the launch velocity. And notice how it doesn't have an x or a y. So that tells you it's not a component vector. It's not an x. It's not a y. It's the angle that we launched it at. So it's our launch velocity. Okay, times sine theta. Well, we know from back here that v sub I sine theta is just equal to v sub yi. So it's the initial launch velocity in the y direction. All right. So really that turns into just v sub y I, okay? And then we get this guy, acceleration of y, or acceleration in the y direction. Well, that's just gravity. That's 9.81. That's what we're talking about, okay? And then times the change in time, all right? And the rest of the equations kind of work that way. Why don't you just go ahead and pause the video, try to see if you can understand how these all work, all right? They work try to see if you can understand where you could replace the v sub I sine theta with your v sub yi. All right, and that's after you do that, it's essentially exactly what we just got done working with. Okay, so pull this up and you can watch this. They do a pretty good job with a little animation, essentially showing you this diagram over here with just a little bit more information. All right, so here's some formulas, other formulas. Here we go. You ready? So the special case of projectile motion. Okay, so this is when we have initial velocity is horizontal only. All right, that's the key. Initial velocity is horizontal only. So that would be, remember at the very beginning of this whole thing we talked about pushing that penny off the desk and it was only going horizontally and then it fell down from there. Okay, as long as our velocity, our initial velocity is only in the x direction, we can use these formulas and they simplify down pretty well. Okay. All right, so that's essentially what happens here. Notice that these guys here are exactly the same things as what you're used to seeing when we talked about kinematic equations in the previous unit. Yeah, okay. And then our delta x is equal to v sub x delta t, just like before. All right. So just a couple of things, then we'll do a couple practice problems and we'll call it good. All right. Projectile motion is free fall with an initial horizontal speed. That's all it is, right? We've already learned how to master free fall. Lots of you guys did very, very well with this on the exam. So you already know how free fall works. Now projectile motion is just free fall with a horizontal launch to it. So instead of just throwing it straight up and coming straight down or dropping it straight down, we're going to be taking this guy and we're going to launch it to the side at some speed, okay? So the vertical, now what you have to remember is the vertical and the horizontal motions are independent of one another, okay? The horizontal velocity is constant. Acceleration, gravity doesn't pulls down. It's not going to slow it down this way. So the horizontal is going to be going constant that way, but the vertical acceleration is constant, all right? So that's why they're separate from one another. Now, if we lived on some funky planet where gravity was pulling at an angle, okay, say like most of the planet was empty space and the core was like off to one side, so most of gravity pulled off to one side, like that would be totally different, and then all of a sudden we'd have to start worrying about projectile motion would work completely different. But we're not on a funky planet, we're on Earth, and it's funky in its own ways, but not in this one. Okay, so we can say that projectile motion, when we talk about it, horizontal motion is completely separate from vertical motion. They don't affect each other. All right. Components are used to solve for vertical and horizontal quantities. So this is, remember, this is the same way of saying separating them into their x and y parts. Okay, so v sub x and v sub y, d sub x, d sub y, a sub x, a sub y, although we won't ever have a sub x. Okay. Time is the same for both vertical and horizontal motion. Well, that makes sense. Let's think about this. If I have if I'm a cliff diver, right? So here's my cliff, okay, and there's like, you know, a sandy beach right here, and then there's the water out here, and I'm gonna, you know, there's me. I'm gonna run and I'm gonna jump off this way, okay. So I'm gonna run. I have to make sure I hit the water and not the ground, otherwise that would hurt, right? So you got to make sure when you're running that you have enough velocity that you don't hit the ground before you hit the water, right? So, but the amount of time you spend falling is going to be equal, right? So no matter how high this cliff is, like say this cliff is 20 meters high, no matter how high that cliff is, it's always going to take me exactly the same amount of time to fall. You can speed it up a little bit based on air resistance, but for our class, remember, we're not worrying about air resistance, so there's no way to speed up or slow down my fall, all right? But, so no matter what I do, no matter how fast I go horizontally, my time is always going to be the same, okay, until I hit either the ground or the water, okay? And then the velocity at the peak is purely horizontal, or v sub y equals 0. And we talked about that a little bit when we sketched the projectile motion. Remember, we talked about that. And when you're right at the peak, you have no vertical velocity. There's no velocity here. We only have our velocity going here in the x direction. All right, practice problem 1. People in movies... Oh, okay. This is very, very similar to the diagram I just drew. All right, people in movies often jump from buildings into pools. If a person jumps horizontally by running straight off a rooftop from a height of 30.0 meters to a pool that is 5.0 meters from the building, was the initial speed the person must jump. All right, so let's see here. Number one thing in physics is always draw a diagram if you're confused about what's going on. So we're going to draw our building. So here's our building. Maybe we should put some windows in it or something. And we'll add like a little door. Okay, there's our door. There's our doorknob. Okay, and so the person jumps horizontally. All right, so we need a little person. All right, this is awesome. And he jumps horizontally, so that means he has no vertical component. So that means, that gives us a hint. That means we can use this special case. This is a special case here because he says he jumps horizontally. We don't have any vertical initial velocity. All right, and he, I forgot my, there it is. And we forgot, oh shoot, the answer showed. It's all right, we'll get the answer. So anyway, and we're gonna jump into a pool. So this building is 30 from a height of 30.0 meters. All right, so 30.0 meters, and then 5 meters away is a pool. All right, pool. All right, 5 meters away. So we need to make sure that we're running fast enough that that we don't hit the pool. If we don't run fast enough, so let's just sketch real quick. If we don't run fast enough, maybe we'll use a couple of different colors. If we don't run fast enough, then we'll come out here and we'll go kersplat there, right? So that's no good. So we need to make sure that we have a high enough vertical velocity or horizontal velocity to start with, that we hit the ground and the right, or we hit the pool and not the ground. So really this comes into two things. We got to think about two things. We got to think about it vertically and horizontally. So think to yourself, well, what am I asking myself here? Well, I'm asking how fast do I need to run horizontally. So a lot of times that's going to give you the hint that you need to start thinking about it vertically first. So I'm going to make a little column here, and I'm just going to say, all right, vertical. So we're going to talk about the vertical first, and then we talk about horizontal. All right, there's lots of different ways to approach these problems. But it almost always comes down to this fact, is like you work it two separate ways. Once with vertical, and then use what you learn from that and use it in the horizontal, or vice versa, depending on what you're being asked for. In this case, we're asked for the horizontal velocity, so that means we're probably going to have to start with the vertical parts of it. Okay, and then we're going to use whatever we learn from the vertical parts to use it to solve our problem in the horizontal area. Okay, so let's think about what we need to get from our vertical parts in order to solve our horizontal. So if we want to know the initial speed, all right, so this units for speed, all right, speed are in meters per second, right? That's our speed. So we need a distance and we need a time. So we need to know how much distance we need to cover and how much time. Well, we know what the distance is, right? The distance we need to cover is 5 meters, okay? So we know for sure that our meters here is equal to 5 meters. All right, that's easy. So we know that, but we need to know how much time. Well, how much time do we need to have? So we need to cover 5 meters in a certain amount of time, but we need to figure out what that is. Well, it needs to be at least as much time as it takes to fall, because if it takes us more than the time it takes us to fall, we're going to hit the ground. We're not going to be going fast enough. Okay, so that's what we're going to find from the vertical components. We're going to find our time. Okay, does that make sense? All right, so let's think here. So we got to find, so what kind of things do we have in the vertical components? Well, we've got our delta x, right? Our delta x is equal to 30.0 meters. Notice that our delta x here, that's 5, but that's our horizontal. I'm talking vertical, so we're going to ignore 5 right now. That doesn't mean nothing to us vertically, right? Vertically, we're just going up and down here. We're living in vertical land right now. Let's see what else. We've got an initial velocity, right? Well, that's equal to 0 meters per second. That's easy. We don't have a final velocity. We don't know how fast we're going to be going. We could certainly figure it out, but we don't necessarily need to, so we just won't write that in there for a second. T, well, T is what we're solving for. We need to know how much time, right? That's what we needed over here. Okay, and then we also have acceleration. And vertical acceleration is easy. It's always negative 9.81 meters per second squared. All right, so that's that. So now we gotta look back at our kinematic equations in order to find an equation that will allow us to use delta x, vi, and a in order to solve for t. So let's see. We have delta y. Yeah, this guy will work here. Okay, now remember, I called it delta x before, but that was a mistake because it's a y value, right? We're talking about up and down. So we'll use this guy here, delta y, and then 1/2 ay, well, that's, acceleration in the y direction, and then our delta t. Nice. So we can just use that. We didn't even need the vi equals at. In fact, if you think about it for a second, the original equation, remember, this is our special case, but the original equation is was delta x is equal to vi t plus 1/2 at squared. Like, that was our original formula. Well, think about this for a second. We changed it. Instead of going left and right, we're talking about y. So really, okay, so that just turns into y. It's the same difference. It doesn't really matter. Okay. What was our vi in this case? Well, it's equal to 0, so that goes away. That becomes 0. So really, we got delta y is equal to 1/2 at squared. It's essentially the same thing. Not essentially, it is the same thing. All right. So anyway, so delta y 1/2 at squared. All right. So our delta y, and maybe I'll change this here just so we don't get confused. Delta y is equal to 1/2 times at squared. All right, so delta y is equal to 1/2, and our a is negative 9.81. All right, and our t, that's what we're solving for. Wait, we should stop this for a second. I'm sorry. We should be doing this like physicists and not like mathematicians. Okay, so remember, physicists, we rearrange equations. All right, so we're going to solve for t. So that means we're going to multiply both sides by 2 in order to get rid of the 1/2, and we're going to divide by a. So we're going to get 2 delta y over a is equal to t squared. All right, then take the square root of both sides, and we end up with t is equal to the square root of 2 delta y over a. All right, well, that's easy enough. So now we can take that guy. I'm just going to jump it up here, give me a little bit more room. So now we're going to plug in. I should probably bring up the words for this so we can reference it. All right, so t is equal to root 2 times our delta y, well, that's just 30, okay, 30, over our a, which is negative 9.81. Now, you might be thinking to yourself, wait a second, if we divide by a negative, we'll end up with a negative and a square root, and then we'll have imaginary numbers, and then we have an imaginary person jumping off an imaginary building, and blah, blah, blah. No. Remember, we're going down 30, so that means that value needs to be negative as well. So we get 2 times 30 divided by 9.81, and then we're going to take the square root of that value there. So that gives us a t value is equal to 2.47. All right. Our t is equal to 2.47 seconds. So that means when we jump from a height of 30 meters, we only have 2.47 seconds till we either go splat on the cement or we go kasploosh in the pool. All right, 2.47 seconds. All right, no matter what. So that 2.47 seconds, remember, we can use this value here to plug in right there. So the speed we need is simply equal to the 5.0 meters divided by our 2.47 seconds. All right, so we'll just take 5 divided by 2.47, and I got 2.0 seconds. And remember, 5.0 has 2 sig figs, so that's got to be 2.0 seconds, which is exactly what they got, and that's because we're amazing. All right, anyway, practice problem number 2. Now this one's a little bit trickier. This one should be fun. All right, so a golfer practices driving balls off a cliff into the water below. The edge of the cliff is 15 meters above the water. All right. So let's think here. So first, let's draw ourselves a little diagram. All right. So maybe we'll make him. He's a golfer, so that means we're gonna give him like a green cliff here. We got a green cliff. All right. So green cliff. All right. There he is. All right. And he's a golfer, so that means they wear a weird color. What weird color is? How about like this weird pink thing? So anyway, so we got our golfer. All right. There he is. All right. And he needs the golf club. For sure. Alright, so there's that. There's our golf club. Nice. Alright, there's our golf club. It looks kind of more like a music note than a golf club, but whatever. Alright, so then we know that he's driving it into water. Alright, so one more color change here, and he's gonna be knocking it into water. Alright. Maybe we'll give him the benefit of the doubt. Cool. All right, now let's start adding in a little bit of our values. What color should I use to do our math? How about red? All right. So the edge of the cliff is 15 meters above the water, so this is 15 meters. That's easy. If the ball is launched at 51 meters per second at an angle of 15 degrees, how far does the ball travel? All right, so 15 degrees. So the ball's here. We're just going to say it started right on the edge, right there. Okay, and it got launched at 51 meters per second at an angle of 15 degrees. So that's pretty shallow. So we'll say like this is 15 degrees. So that's 15. And so boom. So that's 51 meters per second. Okay? 51 meters per second. My vectors aren't really very well represented here. But whatever. Who cares? Okay? Alright, it says, how far did the ball travel horizontally before hitting the water? Now this is interesting, right? So this is kind of the same idea. So remember, we're going to divide our problem into a vertical component and a horizontal component. Now let's think, which one are we going to be solving for first? Horizontally or vertically? Well, what did it ask for? It says, how far does the ball travel horizontally before hitting the water? So that means we need to solve for the horizontal last, because that's what we're going to get to. So we're going to start with the vertical. Does that make sense? I hope so. It asked for something in the horizontal realm. Okay, so that means we got to start in the vertical realm. All right. So, all right. So let's identify what we need. Okay. So we've got this ball. So if we sketch the path, right? So this ball is going to be coming out here, and then he's going to kind of keep going. Gravity's going to come, and then he's going to come back down, right? And he's going to come out this way. And eventually, we want to know until it hits the water, right? So we want to know, boom, how far is this distance here? Right? That's what we're after, that horizontal distance. So we need to know several things, right? We know that velocity is equal to distance over time. If we want to know distance, right, then that means we need to know the other two parts. We need to know time and we know velocity. Once we can rearrange this, right? We can multiply both sides by time, and we can see that distance is equal to velocity times time. So if we can find the velocity in the x direction, we can find the amount of time it was in the air, then we're golden. We're good to go. All right? Does that make sense? All right. So, which is essentially, we could also just look at this. This is exactly the same thing we had before. We had our distance is equal to our v sub x times delta t. Exactly the same thing. Cool? All right, so that's what we got to solve for. So we need velocity in the x direction, and we also need time. Okay? So what can we do here? So now we need to know time in the air. So that's really what we're going to be trying to get to for the vertical factor. All right? So, but we need to think about this real quick. So, well, okay. So what is our delta x? Well, that one's kind of a little tricky, right? Or a delta y, because we're like our delta y from where we start, right? that's kind of like here-ish, right? So after that part, we know we go negative 15, but before that part, it's not so simple, okay? So it's not so simple. So we really can't use that value right now. All right. Let's see. What else do we have? Well, time, right? Time is what we're after originally. We have our acceleration. That one's easy. So negative 9.81. All right. Meters per second squared. All right. So let's see. So we could find our initial velocity, right? We could find our vi sub y, right? All right, but so how would we find that? Well, let's think about this. So we've got our vectors going like this, right? And that's 51. It's going like this. And so that means it would be made up of two vectors, an x vector here and a y vector here, okay? Remember that? And we know that this angle is 15. So we can find the v sub x and the v sub y. All right, so we know from before, remember way back here, right? The v sub y is equal to vi times sine theta, and the v sub xi is equal to vi cosine theta. All right. So if we want to find the y component, then we'll take our vi, which is 51, and we'll multiply it by sine of our angle, which was 15. All right, so 51. So that means our vi in the y direction is 13.20. We'll say 13.20, and then in the x direction, because we're going to need that eventually anyway, we might as well solve for it now, cosine of 15, and so that's 49.26. All right, 49.26. All right, so those are our two components, and we could double check those by squaring each of them, adding them together, and taking the square root. Oops, the square root of your answer. Right, and I got 51.44. There's 0.0004 times. Sweet. So those are our x and y components. So ours is v sub I, y, or v sub I in the y direction is equal to 13.2 meters per second. All right. Now, do we have a VF? No. No, we do not have a VF. We don't know that either. All right. So life's going to get a little bit more complicated here, huh? So we got a v sub I. We need delta t. All right. So let's think about. I wanted you to ponder for a second. Let's think about our delta y here. So our delta y. What is delta y? Well, delta y is equal to the y final minus the y initial. So in this case, what is our y final? Well, our y final is the water down here, right? Okay, and the y initial is up here. So what's the difference between down here and up here? Well, they already told us it was 15, right? So if we stick this thing on a grid and we say, well, this is our 0 line, that means this would have to be 15. So that means the change in the y has to be 15. And we went from 15 to 0. So that means our 0 is our final, and our yi is negative 15, or is minus a positive 15. So negative 15 overall. Okay, so that is our delta y. Well, that makes life a lot easier, right? Delta y equals negative 15. So which formula can we use to solve for time given all this stuff? So let's jump back over. Let's think about our kinematic equations, and we can see we already looked at this one earlier. Okay, delta y is equal to vi t plus 1/2 at squared. All right, that's life. Delta y equals vit plus 1/2 at squared. And notice that we've got vi, we've got a, we want t, and we got delta y. All right, so now let's be physicists, right? And let's plug in and solve for our t's. Now the fun thing is that our equations already solve for t's. Now this is going to be a pain in the neck. We're actually going to have to use b squared plus or minus the square root of a, that thing, the quadratic formula. Man, brain fire hardcore. All right, anyway, so let's start plugging guys in here. So our delta y is negative 15, so that's negative 15. Our v sub I, we already solved, was 13.2, so it'll be 13.2, and remember it's positive, okay, so that's good, times t plus our 1/2 at squared. So that's 1/2 and then the A is negative 9.81, so we can just go ahead and do that. So we'll just take 9.81 divided by 2. We'll say 4.905. 4.905. So plus a negative 4.905, and then that's t squared. All right, now we'll add over, so we'll say 0 is equal to, and let's rearrange this so it's more like a quadratic we're used to, negative 4.905 t squared plus 13.2 t plus 15. Okay, so that is that, guys. So this is our A's, this is our B's, this is our C's. All right, so that means our t would have to be equal to negative b, which is negative 13.2, plus or minus the square root of b squared, so that's 13.2 squared, minus 4ac. So a is that guy, so negative 4.905, and our c is 15 times 15, all over 2 times a, right? Gosh, I hope I'm remembering this right. 2 times negative 4.905. All right. So if we plug that guy in there, let's see. So we get 13.2 squared plus 4 times 4.905 times 15. All right. So that's 468.50, and we take the square root of that. Now remember, here's where life gets a little bit trickier, is we have to think about, all right, so right now I've got, this is what I've got so far. I have my t is equal to negative 13.2 plus or minus my answer of what was in there, which was 21.65. All right, all divided by 2 point, I forgot to do that part, 2 times negative 4.905. Oops. 5, enter. Oh, delete. All right, negative 9. Oh, well, duh. All right, never mind. Negative 9.81. Now we have to think about this. Now, one of these values is going to be a positive value. One of them is going to be a negative value. All right, so if we take negative 13.2 and we subtract 21.65 and then divide by negative 9.81, we get 3.6, or 3 point, yeah, we'll just say, so we get 3.6 seconds, or, okay, or if we do it the other way, where we take the positive value, we take negative 13.2 plus 21.65, all right, divide that by negative 9.81, and we get a negative 8.61. Negative 0.861 seconds. So one of our answers means that we traveled back in time, right? And the other answer is valid, right? So I wonder which one's valid. It's got to be the valid one, which is the positive time, all right? So we know now that our time is 3.6 seconds, all right? I'll jump up here for the horizontal because we're almost done, all right? Or almost done. So horizontal, all right? So we got 3.6 seconds is our total time, all right? So time, let's see, time is equal to 3.6, and our distance is equal to, well, we don't know. That's what we want to find, right? And we know, do we know our initial x velocity? Well, yeah, we do. We saw for it earlier. Remember when I told you we need it? 49.26 meters per second. So now all we have to do is plug it in to that formula before, right? So delta x is just going to be equal to our v sub I x, 49.26, times the amount of time that it was in the air, which was 3.6 seconds. All right. So we'll take our 3.6 times 49.26. We get 177.336 meters. 177. Just call it 177 meters even. All right. So our ball traveled 177 meters before it fell down, and that's exactly what they got. Only they only took 2 sig figs, and they were rounding way early. So it was just kind of a rounding error, but essentially we got the exact same answer. Cool. So that's projectile motion. This stuff's hard. Like, no joke. You got to spend lots of time doing practice problems. Come and ask for help. Please, please, please ask for help. All right. Let me know what you're struggling with so I know what to focus on during class. All right. Yeah, do the practice problems. Okay. This stuff is not easy. Anyway, so yeah, I'll see you on the flip side.